This deck focuses on a safety-critical cargo planning problem: how to stow dangerous goods so that incompatible materials do not interact during a voyage. The goal is not just efficiency. The goal is to prevent catastrophic reactions, protect the crew, and keep the ship compliant with the International Maritime Dangerous Goods Code. We will move tier by tier, starting with a rigorous optimization model, and then progressing to practical heuristics, advanced optimization, and learning-based methods. Along the way, we will connect each method back to the same operational reality: a three-dimensional ship stowage plan with strict segregation requirements. Imagine the MSV Atlantic carrier crossing the North Atlantic. The vessel carries 2,400 TEUs in total, and within that load there are 340 containers carrying dangerous goods spanning all 9 IMDG classes. The cargo planning team must finalize a stowage plan before departure that remains safe throughout a 14-day journey. The key challenge is that vessel motion, storms, and shifting forces can turn a small planning mistake into simultaneous container damage and dangerous interactions. IMDG segregation requirements exist to stop incompatible dangerous goods from being stored too close to each other. If a breach happens and two incompatible substances interact, you can get rapid escalation, including fire spread, toxic releases, and destructive reactions. Beyond safety, there are major operational and regulatory consequences. A single segregation violation can trigger regulatory noncompliance, port rejection, insurance disputes, and severe environmental impacts. This is why segregation is treated as a hard constraint in stowage planning. Segregation is not a flat, two-dimensional problem. Container ships are stacked in 3 dimensions, and vertical separation requirements can differ from horizontal separation requirements. In addition, the ship is divided into holds with different protection characteristics, such as fire and liquid resistance. Each dangerous goods shipment carries codes that drive compatibility rules, so the planner is solving a large constraint satisfaction problem that must be consistent across the entire vessel before departure. We will use a tiered approach to show multiple solution strategies for the same problem. Tier 1 provides the mathematical foundation using a mixed integer programming formulation. Tier 2 introduces a priority-based constructive heuristic. Tier 3 applies particle swarm optimization. Tier 4 uses deep reinforcement learning with a deep queue network. Tier 5 expands to an integrated digital twin. Tier 8 adds value alignment and ethics. Tier 9 explores a quantum approximate optimization approach. In Tier 1, the decision is to assign each container to a specific position in the vessel. The model encodes segregation rules as constraints, including distance-based separation and restrictions that force certain pairs into different holds. The objective function is designed to heavily penalize any segregation violation, while also allowing softer preferences for better positions. This creates a clear hierarchy: safety and compliance first and operational preferences second. Here we define the fundamental building blocks of the model. We have a set of containers, a set of candidate positions on the vessel, and a set of cargo holds. We also include the set of IMDG danger classes from 1 through 9. These sets allow us to formally express where each container can go and which containers must be separated based on their classes and segregation codes. Parameters describe the stowage environment and the rule system. One key parameter is the required minimum segregation distance between a pair of containers. We also need the actual distance between two vessel positions, the mapping from a position to its hold, the IMDG class of each container, and the segregation requirement code for each pair. Together, these parameters translate the IMDG rulebook into computable constraints. The main assignment variable indicates whether container I is placed in position P. This is the core of the stowage plan. A second variable captures whether a pair of containers violates segregation requirements. This lets the model represent violations explicitly and attach a large penalty to any violation, so the optimizer strongly prefers compliant plans. The objective has 2 parts. First, it applies a very large penalty whenever a pair of containers violates segregation requirements using the violation variable. Second, it adds a weighted preference term for assigning containers to positions. This term represents operational desirability, such as preferred holds or locations, but it is dominated by the safety penalty so that compliance remains the priority. This constraint enforces that every container must be assigned to exactly one position. Operationally, it prevents missing cargo and ensures the plan is complete. It also provides structure for the optimizer because it removes ambiguous solutions where a container could be left unassigned or partially assigned. This constraint ensures each position can hold at most one container. It prevents physical overlap in the stowage plan. In practice, this is essential to keep the assignment realistic, because a ship slot cannot be occupied by multiple containers at the same time. This is the key safety constraint. Containers that require separation must be placed far enough apart. The model compares the actual distance between the chosen positions to the minimum required segregation distance. If the distance requirement is not met, the model can mark the pair as a violation, but then pays a large penalty. This mechanism pushes the solution toward full compliance whenever a compliant plan exists. Some segregation codes require that incompatible materials must be in different holds, not just far apart. This constraint captures that operationally. If two containers are incompatible at a certain level, they cannot both be placed within the same hold. This is especially important for high-consequence combinations, where even partial separation within a single hold is not considered safe enough under the rule set. This figure illustrates how segregation considerations map onto a physical vessel layout. You can think of it as showing which positions are close, which are far, and how holds partition the ship. The visual is useful because it makes it clear why the problem is hard. Segregation is about spatial relationships across many containers, not just about labeling containers as compatible or incompatible. This example uses 4 containers with specific IMDG classes. Container A is Class 1.4S explosives. Container B is Class 3 flammable liquid. Container C is Class 8.1 corrosive acid. Container D is Class 2.1 flammable gas. The segregation requirements include away from constraints with a 3-meter minimum distance and separated from constraints that require different holds. This mix demonstrates both distance and hold-based restrictions in a compact setting. In the example, we have 6 available positions across 2 holds. A feasible plan places container A in hold 1 position 1 and places container B in hold 1 position 3, so it is 3 meters from A. Container C is placed in hold 2 position 1 to satisfy the separated from requirement. Relative to A, container D is placed in hold 1 position 2, while maintaining the required separation from A and C. The key takeaway is that feasibility is achieved by combining both spacing and hold separation. Tier 2 shifts from exact optimization to a constructive heuristic. The idea is to build a stowage plan 1 container at a time, making locally sensible choices. The core principle is priority. Containers with more restrictions are placed first, because early in the process the planner still has flexibility. If you postpone restrictive containers, you often get trapped into violations later. The reported computational growth is on the order of the number of containers squared times the number of positions. In plain terms, the method checks many container pairs and many candidate positions. Operationally, that makes it much faster than solving an exact mixed integer model for large instances, while still being structured enough to reduce the typical violation count compared to random placement. This flow diagram summarizes the heuristic loop. First, compute a priority score for each container based on how restrictive it is relative to others. Then, iterate through containers in priority order. For each container, evaluate candidate positions and select the one that minimizes violations against the containers already placed. This code begins by computing priority scores. The score is based on the total segregation requirements between a container and all other containers, which is a proxy for how difficult that container is to place. Then it sorts containers from most restrictive to least restrictive. This ordering is the main mechanism that protects the search from getting stuck later. In the placement loop, each container is tested against all currently free positions. For each candidate position, the algorithm counts how many segregation rules would be violated if the container were placed there. It selects the position with the lowest violation count, assigns the container, and moves on. This is a greedy strategy, but it is guided by a meaningful priority. Ordering. Here we have a 5-container example with reported priority scores. The container labeled E1 is class 1.1 and has score 12. The container labeled C8 is class 8 with score 10. The container labeled F3 is class 3 with score 8. The container labeled G2 is class 2.3 with score 6, and M9 is class 9 with score 2. The higher the score, the more restrictive the container is and the earlier it should be placed. Using the priority order, the reported placement sequence is E1 first, then C8, then F3, then G2, and finally M9. This is designed to protect feasible options for the most constrained items. The reported outcome is a feasible plan with 0 segregation violations. In contrast, a random placement order can produce 3 violations in the same type of instance, showing why structured ordering matters. Tier 3 moves from a greedy method to a population-based search. Particle swarm optimization treats each particle as a complete stowage plan. Particles move through the solution space using velocity updates influenced by their own best-known plan and the best-known plan in the swarm. This creates a balance between exploration of new plans and exploitation of good patterns. A particle is represented as an assignment vector. Each entry indicates which vessel position is assigned to a given container. During optimization, each particle tracks a personal best assignment, and the swarm tracks a global best. Updates aim to reduce violations and improve operational penalties while keeping assignments feasible. This figure visualizes the particle swarm process for this problem. You can interpret it as many candidate stowage plans evolving in parallel. The key is that the swarm collectively searches for patterns that separate incompatible classes, distribute risk across holds, and avoid distance violations. The fitness function combines multiple components. One component counts segregation violations between container pairs. Additional components capture operational considerations, such as distance inefficiency or imbalance in how positions are utilized. The weights determine how strongly the optimizer prioritizes safety versus secondary efficiency measures. This portion defines the particle structure, including the current assignment, velocity, and best-known assignment. It also sets particle swarm parameters like inertia and acceleration coefficients. The algorithm iterates for a fixed number of iterations, evaluating fitness and updating personal best and global best solutions. In this portion, after evaluating fitness, the algorithm updates velocities using both cognitive influence, which pulls toward personal best, and social influence, which pulls toward global best. Then it updates positions accordingly. Because the stowage plan requires unique positions, the algorithm needs additional logic to ensure assignments remain valid. This section highlights the repair step. After velocity-based updates, assignments can become infeasible, for example, by assigning multiple containers to the same position. The repair mechanism restores uniqueness and feasibility. Without repair, the swarm would frequently drift into invalid plans and the fitness evaluation would become unreliable. The reported experiment uses 30 particles for 50 iterations on an instance with 12 containers and 20 positions. The initial random plan has 8 segregation violations with a fitness score of 8,247. After optimization, the reported result is a plan with 0 violations and a fitness score of 156, representing a 98% improvement. The story is that the optimizer learns to separate high-risk combinations across holds while keeping operational penalties low. Particle swarm optimization works well when there are many interacting constraints, because it can search globally rather than committing early like a greedy heuristic. In this setting, violations are costly, so the swarm learns to avoid placing explosives near corrosives and to respect away from distances. The combination of global guidance and feasibility repair helps the method converge to compliant plans. Tier 4 reframes the problem as a sequential decision process. Instead of placing everything at once, an agent places containers step by step. The agent learns from experience. It explores actions, observes whether they create violations or lead to successful full plans, and gradually learns a policy that prefers safe, efficient sequences of placements. The state includes the current occupancy of positions, the list of remaining containers, and a representation of current violations. This state tells the agent what has already been placed and what risks exist. An action is choosing a container and a free position to place it. The reward design is crucial. It must strongly penalize creating violations and strongly reward completing the full placement, with 0 violations. The reward structure shown here uses a large positive reward for completing all placements with 0 violations. It applies a strong penalty proportional to the number of new violations created by an action. It also includes a penalty for placing a container in a suboptimal location and a small step penalty. This combination encourages the agent to finish the plan quickly and safely, not just to avoid violations in the short term. This diagram shows the deep queue network architecture used to approximate action values. The network takes the state representation as input and outputs a score for candidate actions. During training, the agent uses these scores to choose actions and improves the network, so that actions leading to safe, complete plans are scored higher than actions that create violations. This code defines a multi-layer neural network that maps states to action values. It uses several fully connected layers with nonlinear activations. The purpose is to approximate the expected future return of each placement action, so the agent can choose actions that lead to better long-term outcomes. This section introduces the agent structure, including a replay buffer for experience, an exploration mechanism, and separate online and target networks. It also shows how the agent selects actions using an exploration probability, and otherwise uses the network to choose the best action among valid options. This portion covers the learning step where the agent samples a batch of experiences from memory and computes target values using the target network. It then updates the online network by minimizing the difference between predicted and target values. This is the core mechanism that stabilizes learning over many episodes. This portion shows the training loop over episodes. Each episode resets the environment, places containers until completion, stores experiences, and periodically updates the target network. Over time, exploration decreases, so the agent relies more on learned behavior. The result is a placement policy that can generalize across similar stowage instances. The reported training setup uses 15 containers and 25 positions across 3 holds, trained for 5,000 episodes. The trained agent achieves a 94% success rate in finding compliant solutions, compared to a 23% random baseline. Average episode reward improves from -847 to +78. The reported solution time drops from 45 seconds for traditional optimization to 0.3 seconds for neural network inference. The reported policy shows intuitive behaviors. It prioritizes explosive containers for more isolated positions and avoids early actions that create violations that are hard to fix later. It also learns to group compatible materials to preserve space and to keep options open for more restrictive containers that will be placed later in the sequence. Tier 5 expands the scope beyond a one-time pre-departure plan. A digital twin continuously mirrors the physical vessel and its cargo conditions. By integrating sensor data, vessel motion models, and environmental forecasts, the system can continuously assess segregation risk during the voyage and recommend interventions when conditions worsen. A digital twin includes a physical layer with sensors monitoring container integrity and environmental conditions. It includes a digital model that maintains a real-time 3-dimensional representation. An analytics engine predicts risk and recommends actions. A port integration interface supports compliance verification before arrival and can help prevent port rejections due to safety concerns. This figure shows a system of systems view, connecting sensing, simulation, and analytics. The point is that segregation safety is dynamic during a voyage. Instead of treating the stowage plan as fixed, the twin treats it as something that must remain safe under changing conditions like storms, temperature swings, and structural stress. The described synchronization cycle updates the digital model every 30 seconds based on physical sensor readings. Each cycle recomputes risk scores and evaluates whether segregation barriers remain intact. If risk exceeds a threshold, the system can generate restowage suggestions or operational mitigations, so the crew can act before a near miss becomes an incident. In the example, severe weather causes excessive movement in Hold 3, where Class 1.4 explosives are stowed 4 meters from Class 8.1 corrosives. Temperature sensors report the corrosive container rising to 35 degrees Celsius, and stress sensors indicate barrier integrity is compromised. The analytics engine predicts a 23% probability of segregation failure within 6 hours. It generates three what-if options: emergency restowage at the next port, route deviation to a closer port, or enhanced monitoring with crew intervention. The recommended route deviation avoids an estimated $2.3 million in incident costs for an added $47,000 of fuel. Tier 8 adds an ethical lens. Safety compliance is necessary, but ethical optimization asks who bears risk and how decisions are justified. The framework combines outcome-based thinking, duty-based safety principles, and stewardship values. It also emphasizes governance mechanisms like transparency, auditability, and clear accountability for decisions. Ethical constraints can be expressed as requirements alongside operational constraints. Environmental justice means avoiding decisions that shift risk onto vulnerable communities. Worker safety equity prevents systematically endangering particular crews. Transparency requires explainable reasoning for decisions. The precautionary principle applies stricter spacing when uncertainty is high and consequences are severe.